number 5a. And so we are given x to the fourth over x to the fourth minus 1. And our job is to write out the partial fraction decomposition. And then it specifically tells us do not solve for the unknown variable. So we're not actually going to go through and solve this big system of linear equations. We're just going to set up the initial fractions. Okay, so remember that our real goal, this is sort of a mini problem, and the real goal is eventually that we would like to be able to integrate something like this. And so when I first start out with this, I'm taking it out of the integral and saying, okay, I want to rewrite this fraction. It looks like a rational function, and so I want to rewrite this. Very first thing I want to do is look at this and say, okay, is this a proper fraction? And what I notice is the powers are the same on the top and the bottom, so this is an improper fraction. So step number 1, because I have an improper fraction, or an improper rational function, I need to do long division. All right, so I start out, I've got x to the fourth divided by x to the fourth minus 1. And so I ask myself, how many times is x to the fourth going to the x to the fourth? And the answer is 1. So I've got x to the fourth minus 1, and I subtract that off. So what I want to be careful of, and this is the step where a lot of sign errors happen, I want to make sure that I distribute that negative sign all the way through the parentheses. And so I'll mark that in a slightly different color, so we'll change all the signs. And so now I've got x to the fourth plus negative x to the fourth is 0, and I'm left with a 1. And so in the end, my fraction now looks like x to the fourth over x to the fourth minus 1 is equal to my whole part, which is a 1, plus my remainder over the divisor. So 1 over x to the fourth minus 1. Okay, so step number 1 is to make sure that I have a proper fraction. Any questions about that? Okay, so from here, now I'm going to focus on the fraction part. The whole part is done. But my fractional part here, the 1 over x to the fourth minus 1, what I want to ask myself now is, can I factor this denominator? All right, and Andrew, you say yes. How do you want to factor it? Yeah, so this denominator is the difference of 2 squares. So we've got x squared plus 1 times x squared minus 1. And now when I look at this first term, the x squared plus 1, that's irreducible. There's no way I can factor that unless I start using complex numbers or imaginary numbers. But I can factor the x squared minus 1. That guy's a difference of 2 squares as well. So our full decomposition, or our full factoring in the denominator is x squared plus 1 times x plus 1 times x minus 1. Any questions about that factor? Okay, so I've now factored the entire denominator. And so now what I want to do is to break this up into my partial fractions. And so I need to look at my denominator and say, okay, what type of factors do I have? And I notice that every single one of these is unique. There are no repeated parts. I have some unique linear terms, and then I also have an irreducible quadratic. So for my quadratic, I've got x squared plus 1 in the denominator. My numerator is going to have to be ax plus b. So when we have an irreducible quadratic, the numerator has to be linear. And then our next term, the x plus 1, well, that just needs a letter on top, so we'll go with c. And then finally, x minus 1, and I'll toss a b on the top. So we've now written out 1 over x to the 4th minus 1 as a sum of its partial fractions. Are there any questions on that part? Now, if you had written this out and say, put these in a different order up here, your factors, then your letters would be a little bit different than my letters. And that's okay, because in real life, what we would be doing is eventually solving, and we'd figure out what numbers go on top of the x squared plus 1, what number goes on top of x plus 1, and what number goes on top of x minus 1. And so, in the end, your values would still be the same, they just have different labels on them. Yes?
Will that always be the case for an irreducible quadratic?
Yes.
Okay.
Anytime you have an irreducible quadratic, your numerator is always ax plus b. It's always linear.
Okay.
Good. Other questions? Okay, so we're not quite done. Our final answer is that we originally wanted to write out x to the 4th over x to the 4th minus 1. And so my final answer on this one, I need to remember to include the whole part. So we have that whole part. So x to the 4th over x to the 4th minus 1 is equal to 1 plus all the stuff with the letters. Ax plus b over x squared plus 1 plus c over x plus 1 plus d over x minus 1. So this is our final answer for 6.3 part A. Are there any questions about that? So the part that we're not asked to do on this problem is integrate, but if we were going to integrate, then we'd have an integral of all this stuff after we figured out all those letters, turn them into numbers, and we'd want to integrate each individual term separately. Okay. Did that answer your question?
Yeah.
Okay, cool. All right, so now let's take a look at number 15, and Ryan, this was your question? Okay. So number 15. We've got the integral from 0 to 1 of 2x plus 3 over x plus 1 squared dx. Okay. Ryan, you looked at the problem, and what were your thoughts?
I see that the bottom has a higher degree than the top, and there's 2 ways to approach it. I can either take x plus a over x plus 1 plus b x plus 1 squared for the bx plus c over x plus 1 squared, right?
So your question is, how do you set that top part up?
Yeah, because I can either do that or I can factor it out from the get-go on the bottom.
Okay, so your first comment about, I see that the denominator power is higher. That's great. So that means we're not going to worry about long division. We can totally knock that out. All right, so then the next question here is, if we multiplied out the denominator, would its derivative cancel my numerator? I'm guessing probably not, so you could double check that. But so then your next question here, and that would be that if it did, then we could do a u sub. So here, what we've got is a nicely factored denominator. So when you can factor the denominator in a rational function, chances are pretty good that you're going to want to take a try at partial fractions. So this seems like the right route to go. So we're going to look at the 2x plus 3 over the x plus 1 squared. And the bottom's already factored for us, so life is good. And so what I notice is that our denominator is a repeated linear term. So my first fraction is going to be an x plus 1 in the denominator, and I'll have just an a on the top. And when we have this repeated linear term, our next fraction will be x plus 1 squared. And since really all I'm doing is adding one more linear piece of information, then my numerator is still just going to be one letter. All right, so the only time that we have an ax plus b, a linear term on the top, is if we have an irreducible quadratic. All right, questions about that part?
How come it's x plus 1 and then plus x plus 1 squared? How come you separate it like that?
This here?
Yeah.
So whenever, that's the idea of partial fractions, is that we can take the denominator and we can write each term in the denominator as a separate sum. And the technique for when we have a repeated term is that we first have the term once, and then in the second fraction, it shows up twice. And if you had 3, you'd have a plus c over x plus 1 to the third.
So if that was x plus 1 to the third, it'd be those two plus x plus 1 to the third.
Yep, so the third term here would be,
Right.
yep. Okay, other questions about this setup? So this is, okay, so Ryan, I'm guessing that fixed maybe what was going on here.
Yeah.
All right. So from here, we would figure out our A's and our B's. So maybe I'll go one step further and then let you guys work on it on your own. My next step is going to be to find a common denominator. And here's my suggestion, and you absolutely do not need to listen to this suggestion if you don't want to. But my recommendation is leave your original setup as it is. Don't do the common denominator stuff up here, because then when you go back to figure out and write down your terms, you have a lot of other junk written in there and it gets a little bit confusing. So I recommend leaving your original setup alone and don't touch that. Do this as a new line. So we have 2x plus 3 over x plus 1 squared. Now the only thing is that I need to make sure this first term has an extra x plus 1, so I've got a times x plus 1, and then plus b, and my whole denominator is x plus 1 squared. So I found a common denominator. I needed an x plus 1 on the top and the bottom. This first one, I had to do nothing to the second one. So life is okay so far. Are there any questions about that?
You just got rid of the x plus 1, right, on the denominator?
Well, so that's my next job here, is to get rid of my x plus 1 squareds on both of these denominators.
No, from A, I mean.
Oh, from A up here. So what I did is I said a times x plus 1 over x plus 1 squared. So I multiplied the top and the bottom by x plus 1. And once I did that, then I could combine my terms and have the same denominator. Okay. So now I have the same denominators, so I can multiply both sides by the denominators and clear them out. And I have 2x plus 3 is equal to ax plus a plus b. Okay, so at this point, again, my goal is to figure out what a and b are equal to. So I want to compare these two sides. And so it's a good idea for me to group my x's together. Well, that's already happening. I've got this a here. And I want to group my constant terms together, and those are already grouped together as well. So that step is kind of easy on this particular problem. All right, so now I compare. My x coefficient on the left side is a 2. So it better be the case that I have a 2 in front of the x on the right-hand side. So it better be true that 2 is equal to a. And my constant term on the left side is a 3, and on the right side I've got an a plus b. So I know that 3 is equal to a plus b. All right, I'm super happy about this system of linear equations because I already have a solved for. We already know that a is equal to 2, which means that here we have 3 is equal to 2 plus b, and so b must be equal to 1. Okay, any questions about that so far? Okay, so at this point we can now write out a fraction. We know that 2x plus 3 over x plus 1 squared is equal to 2 over x plus 1 plus 3 over x plus 1 squared.
Isn't it 1?
Yeah, that's not a 3 at all. I looked at the b and it looked like a 3, and so I wrote down a 3. So, okay, so that should be b, which is 1. Thank you. Okay. We've now written out our rational function is a sum of partial fractions. Are there any questions on that part?
And just on the
This one here?
no, the one above.
Yep.
All you did was just times by the denominator. Right?
That's right, yeah. That's right. Since I'm multiplying both sides by that denominator and the denominators are the same, they're going to cancel. Okay, other questions? Okay, so we've still done zero calculus. So now the calculus. Let's see, the original one which I erased was the integral from 0 to 1 of 2x plus 3 over x plus 1 squared dx. And so now that I've done all of this algebra work, I can rewrite this integrand. So I've got the integral from 0 to 1 of 2 over x plus 1 plus 1 over x plus 1 squared dx. All right. So at this point, I now have two separate fractions, and they're combined by a plus sign. So it's probably in my best interest to separate this into two separate integrals. So I've got the integral from 0 to 1 of 2 over x plus 1 dx, plus the integral from 0 to 1 of 1 over x plus 1 squared dx. All right, so looking at these two integrals, any thoughts on that first one?
Is it just 2ln x plus 1, of course before I put the limits in, which isn't this problem going to be 0 because we've got ln's of 1s and 0's going on, or ln, sorry, not ln is 0 because it won't come out in the wash, but when we just do 2 times ln x plus 1, and carry ourselves over to the other.
All right, so this seems like a really good idea. So my very, very first thought might be that I'd have to do u substitution here, but we worked on that one last time, and since this denominator is an x plus 1, its derivative will be 1. And so this guy here is going to be 2 times the natural log of the absolute value of x plus 1, and that will be evaluated between 0 and 1. So let's go ahead and continue evaluating this part, and then we'll focus on the next part. I'm just going to put a big line down the middle and eventually add my final values. So on this one, we've got 2 times the natural log of the absolute value of 1 plus 1, minus 2 times the natural log of 0 plus 1. So we've got 2 times the natural log of 2 minus 2 times the natural log of 1. Natural log of 1 is 0. And so this side is 2 times the natural log of 2. All right, any questions about this first integral that we have? Okay, our other integral over here, we've got the integral from 0 to 1 of 1 over x plus 1, the quantity squared. So I can't use this shortcut of knowing that I'm going to have a natural log because of that squared power up here. Any thoughts on what we might do here? So, okay, so I heard two ideas. One is a u sub, the other is an arctangent. The arctangent would work if I had the square on the x, but because it's on the outside, I'd have to multiply that out and it wouldn't look like that.
So you got to do u sub.
Yeah, so we're going to have to use a u sub. So we'll let our u be equal to x plus 1. Our du over dx will be 1, so dx is equal to du. And because I have a definite integral, I'm going to want to change my boundaries. Okay. And again, if you choose to, you can make it into an indefinite integral, solve it, turn it back into x's, and use the x boundaries. I'm going to go ahead and change the boundaries. So when x is equal to 0, our u will be equal to 0 plus 1, which is 1. So our new lower boundary is 1. And when x is equal to 1, u will be equal to 2. So my boundaries are now 1 to 2. And I have 1 over u squared du. Okay, so now I've written this entirely in terms of u's. I've got a u here, I've got a du at the end, and my boundaries are u values as well. So all is good in terms of transforming this integral. The next thing I want to do is ask myself, how am I going to integrate? So any thoughts on that? Yeah, flipping this is going to be a good idea. So getting rid of the fraction. If I just had 1 over u, our integral would be natural log. But we have a larger power here. So our best option is to flip this. In other words, get rid of the fraction. So we have the integral from 1 to 2 of u to the negative 2 du. And now we can add 1 to the power. So we end up with u to the negative 1 divided by that new power, evaluated between 1 and 2. Does anybody need this information over here anymore? Okay, great. Okay, so we have u to the negative 1 over negative 1 evaluated between 1 and 2. In order to plug in my numbers, I'm going to rewrite this. I'm going to put my u in the denominator again. And so I've got 1 over negative u evaluated between 1 and 2. So I can plug in my 2. So I have 1 over negative 2 minus, plugging in the 1 over negative 1. All right, this isn't too bad. I can clean this up a little bit. I have negative 1/2 plus 1, which gives me a positive 1/2. Okay, are there any questions about solving this second integral here? All right, so this problem involves an awful lot of side work. The entire partial fractions was all kind of off to the side. We've done some work for each of these integrals separately, and so our final answer, now that we've done all that work, and it's all on the board, it's all organized, well, it was all on the board, and so our final answer is going to be 2 times the natural log of 2 plus 1/2. So that's a good question. There is no plus c on this one because it was a definite integral. If we had stopped before plugging in the boundaries, if we had stopped here and written the other one in terms of x, then we would add on plus c. Okay, questions or comments about that one?
When you're doing indefinite integrals, when you solve for the a's and b's,
Yes.
depending on which way you do it when you set the linear your system,
Yes.
you can get different coefficients in the answer, right?
Well, so your a and my a might be different, but if my a was whatever was over the x plus 1 should be the same. So even if my a and b had been on top of the other values, that would be okay. Just so long as once you write these out, your fractions should be the same.
So on that, right there, all you did was just bring the negative 1 down and then brought the u down to make a negative on the top.
Oh, here?
Yeah, you just
So-
brought the negative 1 down to make it 1.
Yes. So this is usually a positive 1 now.
Yeah.
Okay. Other questions? All right.